Hi, everyone. Let's go through the Q4 test study guide questions. So before we get started, just a couple slides to get us into it. You can see the topics list here. I'm not going to read you the whole thing. You have that listed for you there. Just keep in mind that a lot of these on the left are kind of the specific Q4 topics. On the right are the fundamental concepts we've kind of been using all year or that we were using leading up to Q4. So you can expect to see all of these concepts show up on your Q4 test. Before we start going through the questions, please keep a few things in mind. First of all, this video is designed to remind you of the main concepts we've covered throughout the Q4. It's not designed to teach them from scratch. I just don't have enough time in this video. You've had about 40 hours of chemistry class in Q4. I can't teach that in like an hour or so. So with that said, if you really don't remember or understand a topic, look on Schoology for worksheets, ask your teacher for help, attend extra help sessions, search your other videos of mine. So again, this is really going to be a fast video to kind of remind you of how you work through these problems, not to really teach you fundamentally. And finally, this video doesn't cover everything you can expect to see on the test. This should be used in addition to studying your class notes, your Texas assignments, 19 through 26, worksheets from class, and or reviewing old tests and quizzes. I want to take a minute and talk through the formulas sheet. You should have this with you as you work through these problems so you can see what you need to memorize and what you don't. And as you can see, there's very little you have to memorize. So you have the combined gas law in the top left. This one doesn't include the N1 and the N2, but if it did, it would be N1 down there and N2 over here. So you should definitely write those in. Keep in mind the combined gas law is used when you have a change in gas, when a gas is being heated or cooled, or when it's being shrunk or expanded, and you're looking for like the new something. And there's only one rule: temperature must be in Kelvin. The gas law below that is PV equals nRT, and you can see R is given as the gas constant, ideal gas constant. That's when you use when you have a gas that's not changing. We have the pressure conversions below that. We have Avogadro's number, which is the number of particles that equals 1 mole. We have the volume of any gas at STP. We have Dalton's law of partial pressures. Everything you see to the right of that, all of those heat constants and heat formulas, don't worry about that. Not going to be on there. We have our electronegativity ranges, which lead you to bond types. In the bottom left, bottom right, we have pH formulas. And here we have the Vesper chart showing the different molecular geometries you could see. Plus in the pack, you'll have your periodic table, activity series, solubility table, polyatomic ions list, and electronegativity values. So you have all this information with you. And without further ado, let's begin. So a chemistry teacher performs a fiery demonstration combusting a small amount of butane, which is tetracarbon hexahydride. Tetra is 4, C4. Hexa is 6, H6. Combusting a small amount of this. Now in a combustion reaction, you're always going to have plus O2 gas yielding CO2 plus H2O. Okay. So the class gathered the water that was produced and found it weighed 52.1 grams. Based on this, how many grams of butane must have combusted? So this is a classic gram-to-gram stoichiometry problem. We were kind of finishing this stuff up at the end of Q3 before we built upon it in Q4. So we're going to start with our mass of water, turn that into grams. Turn it into moles. So 52.1 grams of H2O times 1 mole over 18.02 grams. That's the molar mass of water. 52.1 over 18.02 gives me 2.89 moles of water. Okay, now I need to balance this equation and apply that mole ratio. So when I balance combustions, I always start with H, then C, then O. So starting with my H's, I'm seeing H6 and H2. So I'm thinking of putting a 3 here. But before I do that, I'm realizing that's going to be a problem because putting a 3 there is going to give me an odd number of O's. So when in doubt, double it. So instead of 1 and 3, I'm going to go 2 and 6. And that allows me to now fix my carbons. 2 times 4 is 8. So I'll put an 8 there. For oxygens, I have 8 times 2 is 16 here. 6 times 1 is 6 here. 16 and 6 is 22. So I need 11. All right, giving me a ratio of 2 to 11 to 8 to 6. Okay, we're going to plug the 2.89 right here. we're going to put an X under the butane. I'm going to apply a 6:2 ratio, meaning I'm going to divide that by 3. 2.89 divided by 3 is 0.964 moles of C4H6. All right, let's get the molar mass of that. So 12.01 times 4 plus 1.01 times 6. I'm seeing 52.22. Give me a final answer of 52.3 grams. By the way, just a coincidence that it happens to be almost the same. In fact, I can see what happened here. The molar mass of the butane, 52.22, is almost exactly 3 times the molar mass of water. And since it's a 6:2 ratio, it's like you divide it by 3 that way and then multiply it by 3 that way. So it ended up working out nicely like that. Okay, it's not like mass is conserved in that specific example. It's not like if 52 grams go in, 52 grams come out, because we also have the oxygen and CO2 to worry about. Just a coincidence, it happened to be so close. All right, number 2, balanced equation, including state symbols of the double replacement reaction between solutions of silver nitrate and aluminum iodide. So a bit of a naming practice, bit of a formula writing practice. So silver nitrate is going to be AgNO3. All right, in this video, I'm assuming you know how to do your naming. All right, I'm not going to do step-by-step naming. If you need that, there's worksheets, videos on that. Aluminum iodide is Al(I3), and since these are both solutions, I put aqueous next to both of them. So in a single replacement reaction, the silver is going to react with the iodine, giving us silver iodide, AgI. You check your solubility table. This ends up being solid. The other product is going to be aluminum nitrate, AlNO3, aqueous. Again, I did that quickly, but you check your solubility table, and you'll see that aluminum nitrate, much like all nitrates, that's how I knew it so quickly, is aqueous. So that's our unbalanced equation. And now I'm looking and I'm seeing 3 nitrates on the right. So we'll put a 3 here, 3 silvers, 3 silvers, 3 iodides, 3 iodides, and we're balanced. Question 3, what volume of solution is needed to make a 0.150 molar solution if you have 12.8 grams of potassium chloride? So this is a classic molarity problem. Molarity equals moles per liter. Okay, that's not on the formula sheet, so make sure you note this one. Because we're given the molarity, we're given the grams, and if you're given the grams of something, you can always find moles. And we're looking for volume. So let's rearrange this to solve for liters. So the first thing I would do is just multiply both sides by liters to get this out of the denominator. So molarity times liters equals moles. And now I could very easily get liters equals moles over molarity. Okay. You can also use the triangle if it'll help you, where you put moles on top, and then it doesn't actually matter what you put on the bottom. I tend to go molarity moles liters, and all you do is you kind of cover up with your finger the one you're looking for, and the formula is revealed. So if you cover up the L, you can see it's moles over molarity. All right, so liters is going to equal moles. Now we don't know moles, we know grams. So we got to do a little bit of extra work here. 12.8 grams of KCl times 1 mole over K is 39.098, Cl 35.45, gives me 74.55. 12.8 over that gives me 0.172 moles. KCl. Okay, so liters equals 0.172 moles divided by molarity, which is 0.150. 0.150. Okay, you can put the molarity symbol, or you can write it as moles per liter. And if you do that, you can see the moles canceling nicely. Liters ends up on the top because it's denominator within a denominator. Anyway, 0.172 over 0.150 gives me 1.172 0.15, checking sig figs, 3 sig figs are needed, 1.15. And what's my unit? Liters. The problem doesn't clarify what volume unit you need, so I'll leave it in liters. You can also turn that into milliliters, and you multiply that by 1,000, 1,150 milliliters. Okay, question 4. 16.2 milliliters of a 0.340 molar sodium sulfate solution, really, I guess I don't need to say solution. If I give you molarity, it's implied that it's a solution, is mixed with 12.7 milliliters of 0.400 molar lead 2 acetate. What mass of precipitate will form? Okay, so whenever I see what mass of precipitate will form, I know this is going to be a stoichiometry question, but this isn't classic gram to gram stoich. Look what we're given. We're given the volume and molarity of each reactant. So what type of stoich problem is this? Molarity stoich. So we're going to use the molarity formula, specifically moles equals molarity times liters, to find moles of each of these. And anytime you're given both reactants, it automatically makes it what type of stoich problem? Limiting reactant. We're going to have to identify that. All right, let's start with the balanced equation. So sodium sulfate, Na2SO4 aqueous, reacts with lead 2 acetate, PbC2H3O2 2 aqueous. I believe I'm going to run out of room here. Let me shift this down. All right, so another double replacement reaction. We're going to get sodium acetate, NaC2H3O2. I know that that's going to be aqueous because sodium is always aqueous and acetate's always aqueous. PbSO4. So the lead has a charge of 2+. The sulfate has a charge of 2-. So we get PbSO4, which I believe is solid. Let's confirm. If it's not solid, by the way, it's an invalid question because it would be no reaction if you have aqueous. Lead 2 sulfate solid. All right, so that's our precipitate. The precipitate means the solid product. We need to balance this. So all I need is a 2 there, giving me a 1 to 1 to 2 to 1 ratio. All right, so we need to find moles of each of these reactants. So for our sodium sulfate, I need to multiply the molarity, so 0.340 moles per liter, times my liters, not 16.2, but divide that by 1,000, 0.0162 liters, and that gives me 0.00551. So that goes down here under the sodium sulfate. Okay. We do the same thing for the other reactant, 12. Oh, I was going to do 12.7. That's not correct. We're going to multiply molarity, which is 0.400 moles per liter, times the liter version of that, which is 0.0127 liters. 400 times 0.0127 gives me 0.00508 moles, and that's this one. I was almost going to say, disclaimer, I made up random numbers for these problems without actually working them out, but hey, I got it pretty close, didn't I? So fortunately, it's nice and easy to identify the LR. Make sure you do that. You can't just pick your favorite one of these, and you can't just do one of them. You have to work both of them out into moles, and you go with the limiting reactant to solve for your X. So because it's 1 to 1, it's simply going to be the smaller one. So the answer is that many moles, 0.00508 moles. And now we need grams, right? Yes. So I just need a molar mass of lead 2 sulfate. So 1 Pb is 106, nope, that's palladium, 207.2 plus 1 sulfur plus 4 O's is 64. So I'm getting 303.26. Which gives me a final answer of 1.54 grams. Just make sure I have 3 sig figs. Yes, I do. Let me do a quick double check on that molar mass. 207.2 plus 32.07 plus 64. Okay. All right, question 5. How many milliliters of 6.00 molar hydrochloric acid are needed to make 2.00 liters of 0.100 molar hydrochloric acid? So this is a dilution problem. You start with a very concentrated solution. We sometimes call this a stock solution. And the dilution formula is very simple. Molarity 1, volume 1 equals molarity 2, volume 2. Where the 1s are either the concentrated or the dilute, and the 2s are the other one. So we are looking for milliliters or volume of the concentrated solution. So I'm just going to assign my 6 molar as 1 and my 0.1 molar as 2. It doesn't matter which you assign. So I'm solving for V1. V1 is going to equal molarity 2, volume 2 divided by molarity 1, which in our case is going to be 0.100 molar times 2.00 liters. And we're going to divide that by molarity of number 1, which is 6.00 molar. Think to yourself, what should this answer end up being? If you're looking for 2 liters, are we going to need more than 2 liters of the stock solution or less? Well, it's going to be less, probably much less, because the stock solution is super concentrated and we're only looking for 0.1 molar. So I'm guessing this is going to be much, much less than 2 liters. 0.1 times 2 divided by 6 gives me 0.0333. And what's my unit? Molarity cancels. The unit is liters. Now the problem asks for milliliters. So I'm going to now convert that into milliliters by multiplying by 1,000 and giving us 33.3 milliliters. All right. So that's what you would do. You would carefully pipe that out 33.3 milliliters of your stock solution and put it in enough water to get you to 2 liters. And there's your solution. Number 6, identify the Bronsted-Lowry acid and base and the conjugate acid and base in the following. So remember, by the Bronsted-Lowry definition, an acid is a proton donor and a proton is H+, and a Bronsted-Lowry base is a proton acceptor. So let's knock that out first on the left side. So the H2PO3 minus turns into H3PO3. This one turns into that one. How do I know that? Well, they look very similar. So what did it do? Well, it went from 2 H's to 3 H's, and it went from -1 to 0 charge. So clearly it gained an H+, or it accepted an H+. That's going to make this one the Bronsted-Lowry base, because it accepted the H+, which will make my other one the acid, but let's just confirm. So the HN2 minus turned into N3 minus. So what happened? Well, it lost its H and it also lost a plus charge because it went from 2 minus to 3 minus. So by losing or giving away or donating an H plus, that makes this my Bronsted-Lowry acid. Now on the right side, we have a conjugate base and a conjugate acid. This one, we do a role switch. The Bronsted-Lowry base turns into the conjugate acid. So that's going to be this one. The Bronsted-Lowry acid turns into the conjugate base. And this makes sense because once a molecule or an ion gives away an H+, well, it now has a vacant spot that another H+ could theoretically arrive in. Or if it accepts an H+, it's now holding an extra H+ that it could theoretically give away. And in fact, if you look on the right side and I asked you, which of those 2 products could potentially act as an acid? There was only one answer. It's the second one because it's the only one with hydrogen. Don't forget, Bronsted-Lowry definition is different from Arrhenius definition. The Arrhenius definition simply states that acids produce H+ ions when you dissolve them in water, and bases produce hydroxide ions when you dissolve them in water. Number 7, to demonstrate the difference between strong and weak acids, sketch nitric acid strong in one beaker and hydrosulfuric acid weak in another beaker. All right, beaker number 1. Number 2. So here we're going to have HNO3, that's nitric acid, and hydrosulfuric acid is H2S aqueous. Okay, I'm not going to focus much on acid naming. Just keep in mind If it has hydro in front of it, it's going to be one of those binary acids where it's just H and one other element, like hydrochloric is HCl, hydrosulfuric, H2S, hydroiodic, HI. If it doesn't have hydro, it's going to be one of those either called oxyacids or ternary acids where you have a polyatomic ion. And then you need to consider ate-ic, ate-us. So nitric, ic, comes from nitrate, NO3 minus. So that is why we have HNO3. So make sure you review acid naming. All right, so this one is strong. This one is weak. And acids really are not acids unless they're actively in water, so we'll show that. Now, what's the difference between strong and weak? A strong acid fully dissociates into ions, 100%. It's a one-way process. It splits up and it stays split up. So in this case, we're going to split this into ions. Now, how many ions do we get when we have HNO3? The answer is 2. You're going to get an H plus ion and an NO3 minus ion. Nitrate sticks together as a team. The NO3 are covalently bonded together that makes up one ion that does not separate in water. So H plus, NO3 minus. H plus, NO3 minus. I'll just show a few examples. And then you can show some waters kind of pointing towards the positive ions, away from the negative ions, sort of like we've been doing all year. On the weak side, what's the difference? Well, the difference is that in a weak acid, it only partially splits up. And really a better way of saying it is each of the H2S's are currently splitting up, but then moments later coming back together, splitting up, coming back together, splitting up, coming back together. So at any given time, if you were to take a snapshot of it, you would see some of them split up and some of them together. So when this splits up, we're going to get H plus, technically 2 H pluses, and sulfide S2 minus. So something like this. H plus, S2 minus, that's one that we can show split up. In fact, let's be thorough here. It's diprotic. So let's stick a second H plus there. But then we have to show some that are still together because weak acids do not fully dissociate and stay dissociated like that. So then we could just put some water molecules kind of interacting with the ions. And we could even show them like neutral compared to the molecules. You know, it's not really going to be attracted strongly to either side of that, unless technically that's going to be a polar molecule so that we can get into Vesper later. But technically it would, the oxygen side would be pointing a little bit towards the sulfur side if I want to be super thorough. So that's the difference between strong and weak, fully split up versus partially split up. Question 8. If 63.2 milliliters of 0.250 molar hydroiodic acid are needed to neutralize 14.9 milliliters of sodium hydroxide, what's the molarity of the base? So this is a classic titration problem. You have an unknown molarity base, call that the analyte. You use a known molarity acid, in this case, well, that's going to be our titrant, and we're going to perform a lab, and I guess the lab determined this number right here. That's the volume of acid that was titrated to solve. So for titration problems, I always ask myself one question first. I say, can I use my formula? Molarity 1, volume 1, or I should say molarity acid, volume acid equals molarity base, volume base. I mean, you can even swap those for 1s and 2s, and the question is, can I use that? And it's only true if the acid and the base are in a 1-to-1 ratio. And the way we can tell quickly if it's a 1-to-1 ratio is the number of H's in your acid. If it matches the number of OH's in your base, then it will be a 1-to-1 and you can use this. So hydroiodic acid is HI aqueous. Sodium hydroxide is NaOH aqueous. How many H's in my acid? 1. How many OH's in my base? 1. So we can in fact use this formula and save a little bit of time. If it weren't 1-to-1, you would turn your volume and molarity of the one you know into moles, write out the balanced equation, use stoichiometry to get moles of the other one, and then divide by liters of that one. Just takes an extra minute. Okay, so we're looking for the molarity of the base. So molarity of the base is going to equal, got to get VB out of there, molarity acid over volume base. And now we just plug away. Molarity of the acid, 0.250 molar. Volume of the acid, 63.2 milliliters. Do I have to make that liters? No. As long as I'm consistent, as long as one of the volumes in liters and the others in milliliters, they're going to cancel out. Or as long as they're the same, clarify. Volume of the base, 14.9 milliliters. Okay. Let's solve. I'm expecting my answer to be a very high molarity because you needed a lot of that acid to neutralize a little bit of that base. So the base is probably about maybe about 4.5 times more concentrated. 0.250 times 63.2 over 14.9 gives me 1.06. Yeah, and that makes sense because you needed a lot more of the acid to neutralize a lot less of the base. Question 9. What is the pH of a 92.3 milliliter solution in which 13.2 grams of potassium hydroxide were dissolved? Okay, so there's a lot going on here. I'm looking for pH, but I'm given milliliters and grams of the solution. And I tell you KOH is a strong base, so it fully dissociates. So what we're going to have to do is determine the molarity of this solution. And then from there, we can determine the OH minus concentration and then eventually get us into pH. Because, for example, if I just told you you have like a 0.273 molar NaOH solution, that should have been a lot more straightforward. You should recognize, hey, because NaOH is a strong base that produces 1 hydroxide per NaOH, then this concentration is also going to be my concentration of hydroxide because it's 1 to 1. So let's solve for what our molarity of base is. So remember, molarity equals moles per liter. I have grams of KOH, so 13.2 grams of KOH. 1 mole over 39.098, that's my K, plus my O is 16, plus my H is 1.01, 56.11. 13.2 divided by that gives me 0.235 moles of KOH. All right, so molarity equals 0.235 moles divided by my liters of solution. I have 92.3 milliliters divided by 1,000, 0.0923 liters. And I get 2.55 molar KOH. Okay, so that's extremely concentrated, and I could already tell my answer is going to be greater than 14, because I know just from doing this enough, if the molarity is exactly 1, it's going to have a pH of 0. If it's a base, it would have a pH of exactly 14. So if this is more than 1, so it's actually going to have higher than 14. Okay, so I have my KOH molarity, and like I said before, from this I can determine that the concentration of OH minus, aka the molarity of OH minus, is 2.55 mole, because it's a strong base and you get 1 hydroxide for every NaOH. So for every 1 KOH, you're going to get 1 OH minus. And now I go into my pH formulas. Now, what formula out of those 6 on your sheet there gets us from OH minus concentration into pH? There is none. There is none that will go directly. We need 2 steps here. So you can either take OH minus concentration and turn it into H3O plus concentration using the 1.0 times 10 to the negative 14 formula. Then from that, find pH using negative log. Or I would go what I call the easier route. Turn OH minus into POH and then subtract it from 14. So let's find POH, which is negative log of the OH minus concentration. So negative log of 2.55. This will give us a negative number. Negative log 2.55, negative 0.407. Okay. And the unit of POH is nothing. There is no unit. And now pH is 14 minus POH, so 14 minus negative 0.407. Now, since the 14 in that formula is assumed to be an infinite 14, I'm actually going to assume that's 14.000. So I'm going to actually have my final answer be 14.407. So I end up with 5 sig figs here. Now, if you solve this differently, if you solve it using the other process, you would actually have fewer sig figs in your answer, possibly. I'm trying to do the math in my head. But anyway, that's the gist of this problem. Number 10, what is a hydroxide ion concentration of a 0.030 molar solution of sulfuric acid? Assume it fully dissociates. Yeah, sulfuric acid technically is a, well, we call it a strong acid, but it technically sometimes doesn't fully dissociate because it's sort of strong in the first ionization and not as strong in the second one, but let's assume it's fully dissociated. So if we're given the molarity of this acid, we assume it fully dissociates. What do we directly know about this? Well, because sulfuric acid is H2SO4, this is going to produce 2 H pluses and an SO4 2 minus, right? 2 H pluses and an SO4 2 minus. Now, what do those H pluses do, aka protons? What do those do as soon as they hit the water? Well, these immediately bond with water to form H3O plus or hydronium. So the point is, for every 1 sulfuric acid molecule, how many H3O pluses are you getting? 2. So if my concentration or molarity of H2SO4 is 0.030 molar, what's my H3O plus concentration going to be? Equal to that, half of that, or twice that? It's going to be twice, because for every 1 H2SO4, you're getting 2 hydroniums. So we're going to double that, giving us 0.060 molar. And from here, we can now solve. So anytime you have one formula and you need the other one, you're going to use what I generally call formula 6. Now, if they mean anything, it's this formula. It's that one concentration times the other concentration always gives you 1.0, and this is like an infinite one, times 10 to the negative 14. So we're going to divide this by this to give us this. I'm basically just rearranging the formula to solve for OH minus concentration. All right, so once again, 1.00 times 10 to the negative 14th divided by 0.060, and technically the unit here is molar, and this technically molarity squared. 1 times 10 to the negative 14th divided by 0.060 gives me, checking my sig figs, looks like 2 sig figs. My answer is going to be 1.7 times 10 to the negative 13th, and my unit is molar. Anytime you're asking for the concentration of, that's going to be molarity or molar. Number 11. What volume of oxygen gas can be collected at 1.10 atm of pressure, 34 degrees Celsius, when 46.4 grams of solid potassium chlorate decomposes into solid potassium chloride and oxygen gas? This might sound familiar. This was I grabbed this from UTexas 24 question, modified it a bit. So this is a classic gas stoichiometry problem. We're starting with, we're looking for volume of oxygen gas at that pressure and that temperature. We're starting with grams of solid potassium chlorate. So we're going to do stoichiometry first to find moles of oxygen gas. And then once we have moles of oxygen gas, we also have pressure of oxygen gas and temperature of oxygen gas. And remember, we always know R. We're going to use Pivnert to solve for V. All right, so we start with a balanced equation. So potassium chlorate is going to be KClO3, solid, decomposes into, so there's my yields, solid potassium chloride, KCl, plus oxygen gas. We've got to balance this out. Let's see. I'm seeing 3 O's on the left, 2 on the right. So I see 3s and 2s. I think 2s and 3s. Let me try that. So that balances my O's. And then I just need a 2 there. Yeah, it looks like we're good. 2, 2, 3. All right, we have 46.4 grams of potassium chlorate. 46.4 grams of KClO3. I feel like I've used potassium so many times today. 39.098 plus 1 chlorine plus 3 O's is 48. 122.55. So 1 mole over 122.55 grams. 0.379. Okay, so that's going to fill in under my KClO3, 0.379 moles. And since I'm looking for volume of oxygen gas, I'm going to solve for moles of oxygen gas right here. So it's a 2 to 3 mole ratio. So what do? Multiply it by 1.5 or 3 over 2. So times 1.5 gives me 0.568 moles of O2 gas. Okay. And now I know pressure, I know temperature, I know moles, I know R. We're going to use Pivner now. So PV equals nRT. We're solving for volume, so volume equals nRT over P. N is 0.568 moles. R is 0.0821 liters times atmosphere over moles times Kelvin. That's right on your sheet there. And don't forget, anytime you use this gas law, you have to match those units. So T is temperature. I cannot plug in 34.0 degrees Celsius. I have to turn that into Kelvin. So I can say plus 273.15. So 34 plus 273.15. And since I have 1 decimal place in my Celsius, I'm going to go 1 decimal place in my Kelvin, 307.2. We divide that by pressure, which has to be an ATM, and it gave it an ATM, 1.10 ATM. Let's make sure. So mole cancels mole, Kelvin cancels Kelvin, ATM cancels ATM. We're left with liters, which makes sense. Let's solve. 0.568 times 0.0821 equals times 307.2 equals divided by 1.10. Final answer, 13.0 liters. Checking sig figs, yes. All right, question 12. Long question because this is an interesting one. In the Haber process, nitrogen and hydrogen gases react to form ammonia gas, a key component of artificial plant fertilizer. In fact, this process has been known as the largest saver of human life in history. Why do we have 8 billion people on the planet today? Probably because of this, because up until this process was made, fertilizer was basically manure, and we couldn't figure out how to make artificial fertilizer. But with this process, we formed NH3, which is the main component of fertilizer. And we were able to increase crop yields like tenfold after this. So this is how we helped feed the world in the 1900s and into today. Anyway, also controversial because it was used to make ammonia for bombs in World War I and World War II. So this process developed in the early 1900s requires incredibly high temperatures and pressures. If 5.40 liters of hydrogen gas react with excess nitrogen at 455 Celsius and 200 ATM of pressure, yes, this is actually the pressure required, and the resulting ammonia gas is captured and slowly brought to STP, what volume would this ammonia gas occupy? Long question. Let's see what we're looking for here. Well, it gave us a reaction. Clearly, we're going to need it. So nitrogen gas reacts with hydrogen gas to produce ammonia, NH3, so a gas. Balance it with a 2 there and 3 there. Oh, 1, 3, 2. Okay, what does it give us? Well, it gives us liters of hydrogen gas at this temperature and this pressure. Once again, it gives us liters, temperature, and pressure of the hydrogen gas. What can you determine with those three values? Well, remember, we always know R, so you can determine N. You can determine number of moles, and that's how we're going to start. PV equals nRT. We're going to solve for N, which is moles of, careful, there's a lot going on, it's moles of hydrogen. So N equals PV over RT, PV over RT. So pressure is 200 atm. This is why this was such a hard process. You wouldn't think it would take society, hundreds of years to just mix the two elements together to produce NH3, but you had to do it at 200 atmospheres of pressure. Volume, 5.40 liters divided by R, 0.0821 liters times atmospheres over moles times Kelvin. And T, 455 plus 273.15, the 0.15 will get cut off because we're going to the nearest whole number here, 728 Kelvin. So 200 times 5.40 equals, divided by 0.0821 equals, divided by 728 equals 18.1 moles. And that's moles of what? It's moles of hydrogen. All right. And the resulting ammonia gas is captured. What volume would this ammonia gas occupy? So we're looking for ammonia. We're starting with 18.1 moles of hydrogen. We're assuming the N2 is in excess. So what's my mole ratio here? It's 3 to 2. So we're going to divide by 2 and multiply by 3. Yes, or the way I would say it is divide by 1.5. So divided by 1.5 gives us 12.0. That's what I get, 12.046. I'll call it 12.0 moles of NH3. Okay. Now, what are we looking for about the gas? Well, we're not looking for its moles and we're not looking for its mass. We're looking for the volume if it's brought to STP conditions. Now, at first glance, you might say, ooh, combined gas law problem, because we're changing the conditions. Well, this is technically not going to be combined gas law here, because we would have to solve for the volume of that gas now. The easier way to do this is to just say, if this many moles doesn't change and it suddenly becomes STP, what is this many moles going to occupy at STP? And we can actually use a shortcut here. Remember, on the front of your answer sheet or your reference sheet, you have 1 mole of any gas is 22.4 liters. This is only true at STP. We can just use what I call the STP shortcut. You can just multiply this by 22.4 liters per mole. And this is going to give you 12 times 22.4. Sig fig check, looks like 3 sig figs, 269 liters of ammonia gas. Notice a tiny amount of hydrogen gave you an incredibly large amount of ammonia. That's mostly due to the pressure. You can think of the pressure of a gas as almost like its density or its concentration in a way. If it's that pressurized, it must really be crammed into a small container. All right, definitely a tough problem, but we made it through. Question 13, a sample of gas has a pressure of 528 mmHg at 21 degrees Celsius. It is cooled to -79. What is the new pressure? So I could tell this is going to be a combined gas law problem because I have a starting pressure, a starting temperature, and a final temperature. So P1 V1 over T1 N1 equals P2 V2 over T2 N2. That's how it's written on your starting sheet there. We can also write it this way. P1 V1 T2 N2 equals P2 V2 T1 N1. I prefer this because it gets rid of those denominators. All right, so our starting pressure, P1, is 528 mmHg. Our starting temperature, T1, is 21 degrees Celsius. Our final temperature, T2, is negative 79 degrees Celsius. Right. Now, what are the rules here? Do we have to use liters, ATM, moles, Kelvin? No. Pressure one is fine in mmHg because we're looking for, it just says pressure. We don't need it in ATM. But temperature does have to go into Kelvin. So we're going to add 273 to each of these. 21 plus 273 is 294. Negative 79 plus 273 is 194. All right. So I didn't give you any values for temperature. No, sorry, I did, obviously. I didn't give you any values for volume. So what are we assuming? In fact, I'm getting into this. What are we assuming? Well, we're assuming volume is held constant. So I can just remove that from both sides. And what else did I not mention? I didn't mention moles. So we assume that the moles are constant. So we can get rid of those as well. So my formula ends up being P1T2 equals P2T1. We're solving for the new pressure. That's going to be P2. So P2, we got to get T1 out of there. P1, T2 over T1. And using our numbers, P1 is 528 mmHg. T2, 194 Kelvin. Divided by T1, 294 Kelvin. 528 times 194 divided by 294 gives me 348. And my unit is mmHg. These cancel. That's my new pressure. So again, the second question says, what must we assume is held constant? That's going to be the volume and number of particles, because I didn't mention either of those. And finally, explain why on the particle level, the answer you got makes sense. In other words, why, when we cool a gas from 21 to negative 79, does it go from this pressure, 528, to this pressure, 348? Why does it drop? Well, remember, temperature is all about speed, and pressure is all about collisions with the walls of the container. So we cooled our gas down, so we slowed it down, which means you're going to have fewer and less powerful collisions with the inside walls. So that's why it makes sense that our pressure dropped. Okay. Looking at the time here, might get through these, might need to break this up. Number 14, what is the pressure of a sample of helium gas that has that many grams of gas occupying a volume of 457 milliliters at standard temperature? Answer in units of torr. Okay, we're looking for pressure. We're given grams. What do we almost always do with grams? Turn it into moles. So essentially we're given moles. We're given volume. We're given temperature. What can we use to find pressure? We're going to use PV equals nRT. Notice there's no changes happening here. It's just a kind of straight up plug and chug problem where we just plug the values in and get our answer. All right, so PV equals nRT. We're solving for pressure. So pressure equals nRT over P. Let's just plug right in here. So for moles, I have helium gas, this many moles of it, this many grams of it. So 0.158 grams of HE, times 1 mole over, just using helium, 4.00 grams, which gives us 0.158 over 4, 0.0395 moles. R, 0.0821 liters atmospheres over moles Kelvin. T is temperature, standard temperature, that's 0 degrees Celsius, but you can't plug that in. You have to plug in 273.15 Kelvin. We divide that by pressure, which is, no, I did my formula wrong. Obviously, I don't divide this by pressure. I divide this by volume, which is 457 milliliters. But remember, you have to match the units of R. So that has to be turned into liters, 0.457 liters. All right, let's check our units. Mole cancels mole, Kelvin cancels Kelvin, liter cancels liter, and we solve. 0.0395 times 0.0821 times 273.15 divided by 0.457 gives me a pressure of 1.94 ATM. And it has to be ATM because that's the unit we got. But notice the problem says answer in units of torr. By the way, I couldn't have just kept it in torr because I'm looking for torr. You cannot plug torr into this gas law. We have to convert we have to get the pressure in ATM. I guess that doesn't really apply to what I said. I can't just assume this is torr. So I get my ATM here, and I'm going to multiply that by 760 torr over 1 ATM. The 760 is assumed to be true by definition, so 3 sig figs or infinite sig figs, really. So 1.94 times 760 gives me 1474.4 with 3 sig figs, 1470 torr. Question 15. A sample of hydrogen gas is collected through water displacement. The room, was there a second part to this one? No. The room pressure is 771 mmHg, and that is assumed to be the pressure of the gas collected. This hopefully brings back memories of the molar volume of gas lab. The partial pressure of water at the recorded temperature is 18 mmHg. What's the partial pressure of the hydrogen gas? So this uses Dalton's law. P total is pressure of all the partial, the sum of all the partial pressure. So in this case, this gas consists of H2 and H2O. So that's our basic setup with Dalton's law. We're solving for pressure of the H2. So that's going to be pressure total minus pressure of H2O. The total pressure is 771. We subtract the pressure of water, which is 18. 771 minus 18. 753 mmHg. Very simple Dalton's law problem. Question 16. All right, so we have trends on the periodic table. So the first trend we're looking at is potassium, cobalt, and selenium. So potassium is number 19, cobalt is number 27, so number CO here, and selenium SE is 34, and these are all in a row. And I purposely picked them to be in a row, and I should say they're in the same period. So let's look at the trend from left to right across one period of the periodic table. So the trend from smallest to largest atomic radius. Remember, the trend as you go from left to right is the atoms actually shrink down in size, which is counterintuitive. I mean, of these three, selenium has the most protons, the most neutrons, the most electrons. One would expect it to be the biggest, but it's actually going to be the smallest. So we're going to have here the largest radius to the smallest radius. Or technically, if you want to rank them from smallest to largest, you would rank it as SE followed by CO followed by K. Okay. Now, why does the size shrink? Because you have more protons in the nucleus that pull that outer orbital or shell or ring of electrons in. The next trend is ionization energy, lowest to highest ionization energy. Remember, that's the energy required to lose an electron. Which of these is the most likely to lose electrons? It's going to be potassium on the left. We say things all year like potassium wants to lose a valence electron. It wants to get rid of it. Well, what we really mean is it very easily gets rid of it. It's due to the fewer number of protons there. So we're going to have the smallest or lowest, I'll say IE for ionization energy, going to the highest ionization energy. I mean, think about selenium. Selenium's a non-metal. If you try to steal selenium's electron, of which it has 6 already, is it going to put up a fight? Yeah, it has 6. It's trying to gain 2 more. So obviously it's going to put up a fight if an element tries to steal its electron. Or to put it in a more real context, it will require an incredibly high amount of energy to remove that electron, which means it basically doesn't happen. Nonmetals gain electrons, they don't lose. And lastly, electronegativity. So electronegativity is it's a number that ranks how strongly an element will attract new electrons. I sometimes call it the strength of the element. So this trend, you remember, what's the 4.0 GPa of the periodic table? Fluorine. Fluorine is the most electronegative element, and the trend moves down from there. To the left, it goes down, and down, it goes down. So selenium, being further to the right, is going to have the highest electronegativity. So lowest, I'll say En for electronegativity, going into highest electronegativity. All right, so again, if you wanted to get a straight up answer here for atomic radius, the trend would be Se, then Co, then K. For ionization energy, the rank would be K, then CO, then Se. And for electronegativity, it's also going to be K to CO to Se, like that. All right. 17, so we're looking for the same rankings for Mg, Ca, and Sr. I believe this will be the last one, because as you can see, it's 8:11 on a school day. I'll follow up with a quick one after this. So Mg, Ca, Sr. Why am I writing them this way? Because that's how they look on the periodic table. We're moving down a group here. That group's called the alkaline earth metals. So we're comparing the trends here. So when it comes to atomic radius, what's the trend as you move down a group from one period to the next? The trend is they get larger. Why do they get larger? Because every time you move down to the next period, you're increasing, you're getting an entire new shell or ring or orbital of electrons. So the size is going to increase. So we can say increasing radius. Or if I want to answer the question, if I want to rank them from smallest to largest, the ranking would be Mg, then Ca, then Sr. Okay. The next trend was ionization energy, the energy required to remove an electron. Now, these each have 2 valence electrons that they want to get rid of. They're going to put up very little resistance to that. But which one wants it more? Which is going to put up the least fight? And that's going to be strontium. Why is it easier for strontium to lose its 2 electrons than magnesium? Because strontium's 2 electrons are much farther from the nucleus. There's a greater distance there, and there are more electrons in between that kind of shield it. So the order down here is going to be decreasing ionization energy. So our trend in ionization energy from smallest to largest is going to be Sr, followed by Ca, followed by Mg. And the last trend is electronegativity. And we tend not to think about electronegativity, really, at least I don't in terms of metals. I tend to think of my nonmetals, but I can still relate the trend here. So on the periodic table, and you can see it on your, this is basically given to you with the table. You can see that as you go down a group, the electronegativity values are going to decrease. So it matches ionization energy. So we can say decreasing IE and En, which means our electronegativity trend is going to be the same. Okay, so we're going to stop this here because I have class coming in. I will post a little follow-up for the last 3 shortly.